Welcome to section 5.7. We're going to revisit inverse functions and especially how they relate to polynomial functions that we've been working with. So we're going to find the inverse of invertible polynomial functions. Oh, it doesn't say rational functions, but rational functions too. Let's write that up there. And we're going to, if we need to, we're going to remember how to restrict the domain to find the inverse of a polynomial function. All right, well, let's recap some stuff we know about inverse functions. Inverse functions. Number one, not all functions have inverses, right? Only one-to-one functions have inverses, and we can tell a function is one-to-one to see if it passes the horizontal line test. Now remember, the vertical line test was to test to see if it was a function or not, but for it to be a one-to-one function, remember it had to pass the horizontal line test. We can force a function to be invertible by restricting its domain to a domain on which it is one-to-one. And one more thing to remember about inverse functions, you can check to see if two functions are inverses of each other by composing them and seeing if we get x out. And remember how we found inverse functions? We swapped x and y, solved for y, used inverse function notation. All right, the new stuff we're going to talk about today are radical functions. Radical functions are the inverses of polynomials. Much like how when we saw before we took the f of x equals x squared, when we found the inverse of x squared, we got root x for x greater than or equal to 0. Remember, we restricted the domain of x squared, and we found that root x was its inverse function. So if the polynomial has an even power, we're going to have to need to restrict the domain. And a good way to check is to just look at the graphs. So let's get started with some examples on this. All right, so let's look at an example. Number one, we're going to find a domain in which the function f of x equals x plus 1 squared minus 2 is invertible. Then we're going to find the inverse, and that should say f of x. I'll just fix it. Find the inverse of f of x. And lastly, we're going to practice function composition to check to make sure they're really inverses of each other. All right, so here, graphed in green, is f of x equal to x plus 1 squared minus 2. And if we think about it, it's the x squared function shifted left 1 and down 2 using our function transformation knowledge. All right, so we need to find a domain on which this function is going to be invertible. Because right now it is not passing the horizontal line. Well, that's not a horizontal line. That was terrible. Let's try that again. If we draw a horizontal line, it's going to hit here and here. And so it's not one-to-one. It's not passing the horizontal line test. So we need to think about restricting the values, chopping off half the function so that it does pass the horizontal line test. And usually with quadratic functions, we just start at the vertex and go over. So if the vertex is here at -1, if we chop off and just use the right part of this function, so that is x greater than or equal to -1, then we can see that that function is now invertible. It is now one-to-one because we're just going to ignore this left-hand piece. We're just going to start the function here and do this right-hand swoop up. So that's going to be our restricted domain. So we're going to restrict the domain to be x greater than or equal to -1. All right, so we've restricted our domain to where the function is one-to-one. Let's go ahead and find the inverse. Remember, the first step is to write y instead of f of x. So y equals x plus 1 squared minus 2. And now we swap our x and y's. X equals y plus 1 squared minus 2. And now, now we just solve for y. All right, so we need to undo things until we get y by itself. Well, the outermost thing is this -2, so we're going to add 2 to each side. That gives me x plus 2 equals y plus 1 squared. Sort of opposite order of operations. Now the most outer thing is the square, so we're going to square root both sides. All right, square root of x plus 2 equals y plus 1. And now we're going to subtract 1 from each side. Now be careful, the subtract 1 is not under the square root. You already took the square root. The 1 wasn't part of it. So it's the square root of x plus 2 under the square root sign, and the -1 not under the square root sign. All right? And that is our inverse function. So now we can write f inverse of x equals square root of x plus 2 in your square root minus 1. All right, so now let's check to see if they truly are inverses of each other. So we're going to compute f of f inverse of x. So that would be f of square root of x plus 2 minus 1. Now in our original function f, let's scroll zoom out just a little bit so we can see it. Everywhere we see an x, we're going to write that square root of x plus 2 minus 1. So left parenthesis, square root of x plus 2 minus 1, I'll even put that in another set of parentheses, plus 1 squared minus 2. So I just plugged into my function up here, and then for x, I put in this whole business of the f inverse. Now I simplify to hopefully get x at the end of this. Oh, too far. Equals, inside my parentheses, I have square root of x plus 2 minus 1 plus 1. So that's just going to be the square root of x plus 2. The minus 1 and the plus 1 cancel each other. Squared minus 2. Well, the square root and the radical cancel each other. So that gives me x plus 2 minus 2, which gives me x. Awesome. That's what we are hoping for when we compose the functions. On your own, I would like you to compose f inverse of f of x. Double check that it equals x. All right, let's go on to example 2. All right, this example is g of x is 2x cubed plus 1. First, we want to find a domain in which it is invertible, and then we're going to find the inverse, and then we'll compose to make sure they're really inverses of each other. Well, if we look at this function, the question is this function one-to-one? Is this one-to-one? Does it pass the horizontal line test? It seems to everywhere, but maybe right here. And it actually really does pass the horizontal line test. It gets really flat, but it doesn't get completely flat. It's always increasing a little bit because as you cube things, they're going to get just a little bit bigger. So this was our question mark. If you go into Desmos and graph this function, you zoom in and zoom in and zoom in. I think you can convince yourself that it never really gets truly horizontal. So this is not truly horizontal. It's flat-ish, but it's not truly flat. So this guy is in fact one-to-one the whole time. So the answer is yes, this is one-to-one. So let's go ahead and do the algorithm to find the inverse. We write y equals 2x plus 3, 2x cubed plus 1. I know what I was talking about. Switch x and y. X equals 2y cubed plus 1. And now solve for y. Subtract 1 from each side. X minus 1 equals 2y cubed. Divide by 2. Remember, we're doing inverse, the opposite order of operations. X minus 1 over 2 is y cubed. How do I undo y cubed? Well, I take a cube root. And so my inverse function, this is g inverse of x is the cube root of x minus 1 over 2. Cube root of x minus 1 over 2. And we'll check to make sure they're inverses. I'll do one way. I'll do g of g inverse of x. So that means I'm taking g of the cube root of x minus 1 over 2. So in my original function g, which is 2x cubed plus 1, everywhere I see an x, I'm now going to write this cube root thing. So it's 2, here's my x, cube root x minus 1 over 2 cubed plus 1. All right, let's simplify this. Well, the cube root of x minus 1 squared cubed, these guys cancel, and we get 2, x minus 1 over 2 plus 1. The 2's cancel, and we get x minus 1 plus 1, which equals x. So we're happy. You guys can do it the other way to check on your own. All right, a couple more examples. Let's take a look at this guy. Let's find the domain on which h of x equal to the fifth root of x minus 2 plus 7 is invertible. And then we'll find the inverse. All right, here's the graph. I like looking at the graph. And it looks to me like this guy is one-to-one already. Already one-to-one. It seems to me that it passes a horizontal line test. It looks pretty flat as you go out. But remember, that's sort of asymptotic behavior. And it really is on this side, increasing, increasing, increasing just a smidge and decreasing, decreasing, decreasing. So it never gets truly flat. So this function is already one-to-one, so we just need to find its inverse. So we write y equals the fifth root of x minus 2 plus 7. We switch x and y. And we solve for y. So the first thing I'm going to do is I'm going to work outer inner from outer to inner. I'm going to subtract 7x minus 7 equals the fifth root of y minus 2. Undoing as I go along, the next is the fifth root. How do I get rid of the fifth root? Well, I take it to the fifth power. X minus 7 to the fifth equals y minus 2. The fifth and the fifth root cancel each other out. And finally, I add 2 to each side. X minus 7 to the fifth plus 2 equals y. And that is my inverse function. What was the name of this guy? So h inverse of x equals x minus 7 to the fifth plus 2. And let's just take 10, 20 seconds here to think about what's going on. In my original function here, up here, let me switch colors. In my original function, I took my value, I subtracted 2 from it, I took the fifth root, and I added 7. In my inverse function, I subtract 7, I fifth it, raise it to the fifth power, and then I add 2. And you can see that those steps are in the opposite order. You know, if you go through the steps, they're in the opposite order, and that's what makes inverse functions. Because up here, the first thing I did was right, so we'll see in the original function, the first thing, if you put in a value for x, the first thing you would do would be subtract 2. The second thing you would do would be to take the fifth root. And the third thing you would do would be to add 7. If we look at the inverse function, we put a value in for x, the first thing you would do would be the opposite of the last thing you do before, which is subtract 7. After you subtracted 7, you would raise to the fifth, right? And the last thing you would do would be to add 2, okay? So these are the opposite, all opposite operations in the opposite order. All right, one more example for this guy. Let's find a domain in which our function r of x is invertible. It's a nice rational function, and then we'll find its inverse. Well, again, this guy is already one-to-one. Already one-to-one. We don't have to modify the domain on this one. Really only have to modify the domains on like even polynomials. Those are the ones you're going to have to watch out for. Sometimes on rational functions, you're going to have to modify the domain. Those can be kind of tricky too. But this one, you don't need to modify the domain. It's already passing the horizontal line test. So let's go ahead and find that inverse function. So the first thing we do is we write it as y equals, and then we switch x and y. X equals y plus 4 over y plus 5. Now this one looks a little tricky. People want to do some really crazy simplifying in this. They get carried away and they want to like cross out the y's right away or something. But you have to remember that there are grouping symbols on the top and the bottom of the fraction. And sometimes it helps me if I go ahead and just write in those parentheses when I'm working with these to make sure I don't make mistakes by ungrouping those when I'm not supposed to. And another thing I like to do on this is the first thing I like to do is I like to think about cross multiply and divide. A lot of people have heard of cross multiply and divide before, and this is it. You use it to solve ratios, and in fact, this is actually a ratio too. So I'm going to use it to solve here. So instead of just writing x, I'm going to write x as a ratio of x to 1, and then I'm going to cross multiply, and that gives me x. Oops, why did I quit writing x times y plus 5 equals 1 times y plus 4. Really what I just did was I multiplied both sides of the equation by y plus 5, but sometimes the cross multiply makes people feel better. All right, so let's distribute x here. That's x. Oops, I lost my pen somehow. So let's distribute x here. That's going to give me xy plus 5x equals y plus 4. Let's get the y's to one side and the non-y's to the other. So minus 5x from each side. Xy equals y minus 5x plus 4. Subtract y from each side. Xy minus y equals minus 5x plus 4. Now what I'm going to do is I'm going to factor out a y, leaving x minus 1 equals minus 5x plus 4. So I pulled the y out. That left x in the first term and minus 1 in the second term. Divide both sides by x minus 1. And my inverse function is minus 5x plus 4 over x minus 1. All right, so that is my inverse function for our r inverse of x equals minus 5x plus 4 over x minus 1. All right, so we can try to compose this with our original function. It is a little bit trickier, so hang in there with me. We're going to find r of r inverse of x. So our original function was x plus 4 over x plus 5. Now everywhere I see an x, I'm putting a minus 5x plus 4 over x minus 1 plus 4 over minus 5x plus 4 x minus 1 plus 5. So my original function r, everywhere I see an x, I'm now putting the inverse function. All right, I'm going to have to add some fractions here. So I'm going to multiply 4 by x minus 1 over x minus 1, and the same for 5, because I need to get those common denominators, right? I need to get those common denominators. So that tells me that r of r inverse of x equals minus 5x plus 4, and then let's multiply these out, plus 4x minus 4 over x minus 1 over minus 5x plus 4 plus 5x minus 5 all over x minus 1. All right, let's do some simplifying. Looks like we're going to get somewhere. Well, the 4's are going to cancel, right? And the minus 5x plus 4x gives me minus x over x plus 1. And in the denominator, I'm going to get, let's see, the minus 5x and the plus 5x cancel. The 4 and the minus 5 give me minus 1 over x minus, that should have been a minus 1. X minus 1, x minus 1. And now dividing by minus 1 over x minus 1 is the same as multiplying by x minus 1 over minus 1. So instead of dividing, I multiply these out. These guys cancel, the negatives cancel, and I get x over 1, which is x. Whew. So those are a little bit harder to work out, but you can work through them. All right, that's my last example. You can do the r inverse of r of x on your own.